Hey there, how's it going? Time to do another engineering mechanics problem. This time we're going to look at internal actions. Okay, so here we have the problem. So it's just a bent structural component with a distributed load acting on it, supported by a pin connection at B, supported by a roller at C. We've also got a horizontal force here at C, and we're asked to determine the internal actions at point A. Now, the reason that we might want to do this is that eventually we want to calculate stresses. And as you'll find out if you don't know already, in order to calculate the stress in a component, we need to know the internal actions that are acting at that location. All right, so this is kind of just a step towards analysing this component or structural components in general. So the step to calculating stress is to determine internal action. So this is a problem that just looks at calculating internal actions. All right, so let's make a start on the problem. So the first thing we need to do is to determine all the external loads that are acting on the body. So we've got some applied loads, which are our uniformly distributed load here and the force P, but we've also got external loads that are exerted by the supports. So the roller support at C and the pin connection at B. So we need to know what they are. So we need to draw a free body diagram of the whole structure, put on our loads, and then start to work out our reaction forces. So at the roller here, we're going to have a vertical reaction, no horizontal reaction because it's a roller. And at the pin down here at B, we've got two force reactions, a vertical force and a horizontal force. So the horizontal force here, RBX, we can see that's going to need to be to the left because the only other force acting to the right is P up here to the right. So that one's going to be to the left. How do we work out whether RBY is going to be acting upwards or downwards? If we imagine that we take moments about point C, the distributed load is tending to cause this to rotate anti-clockwise about C. But then we've also got this RBX tending to rotate anti-clockwise about C as well. So for RBY, it's perhaps a little bit difficult to work out. So let's just show it acting vertically upwards. All right, so once we've got that, once we've drawn our free body diagram, we can start to apply our equations of equilibrium. So if we take moments about point B, our two unknowns RBX and RBY both pass through point B. So therefore, they have no moment. So that'll just leave us with RC as an unknown in our equation. So let's work through that. So RC, its perpendicular distance is 2A, tending to rotate anti-clockwise about point B. So therefore, that's positive. Then we have our force here, P, at a perpendicular distance of A, and that's tending to rotate clockwise about point B. So that's negative. And then we have our distributed load here. So you may not be familiar with how to deal with a distributed load, but for a uniformly distributed load like this, its resultant is the magnitude of the distributed load. So this will normally be in newtons or kilonewtons per meter if we had numbers put to this rather than just a variable W. So to get the total load that's generated by this distributed load acting over this full length here, it's just the force per unit length times the length. So we just multiply it here by 2A. And then to do moments, work out what the moment effect of this force or this distributed load will be. The resultant force acts through the centroid of this area of loading. Okay, so for a uniformly distributed load like this, the centroid is just at the geometric center of this distributed load. Okay, so distance here from B of A in this case. So here we'll have W, so the distributed load per meter times the length over which it acts, so 2A, times the distance that the resultant acts from point B, or the perpendicular distance. Okay, and it's tending to rotate in a clockwise direction about point B. So again, this one's negative. So that's all we have. So we can put all that equal to 0, rearrange the equation and solve for RC. All right, so let's go to the next bit. Sum of the forces in the horizontal direction equals 0. So we only have RBX and P here, so it's pretty easy to just write down RBX equals P straight away there. And then sum of the forces in the vertical direction equals 0. We have RBY, the distributed load, and RC. So we put all that into our equation of equilibrium. Okay, so again, just dealing with our distributed load here, just force per unit length times the whole length. Rearrange that, substitute for RC. So we've got RC up here, we've just substituted that into the equation, and we can solve for the vertical reaction force RBY. So now to determine the internal actions, we need to take a cut, or imagine that we take a cut through the section where we want to know the internal action. So at the point that's labelled point A in our problem. And then we draw a free body diagram of one side or the other of the cut. In this problem, I'm going to do both sides just so you can see what happens. But first, we're going to look at the right-hand side. So what we do is we imagine that we've taken a cut through the section. So let me just go back to what we had before. So we've taken a cut through here, through point A. Now, it doesn't matter if we take a cut in this angle or this angle, but usually we'll take a cut that's perpendicular to the longitudinal axis of the structural component that we're analysing. Okay, so that's what I've done. Just take a vertical cut here through point A. All right, so I've drawn the right-hand side here with all of my external loads showing, and note that in doing so, I've put back onto the free body diagram the full distributed load here. I haven't just left the resultant W times 2A at point A here. So we need to make sure that when we're doing the free body diagram of the cut section, we need to look at the distributed loads acting over that section. Internally now, we're going to have generated here internal actions. So there could be axial force, shear force, bending moment, torsional moment in general, generated in here by these external loads. So if I just go back to my previous drawing again, so what we're trying to imagine is that we've got these loads out here transmitted through the body to our support here. And at each location, in general, the internal actions will change as we go along. So I think you can imagine that if we did really take a cut through here, then obviously the structure is just going to collapse, all right? So, or if you imagine that we did cut it through here and then glued it back together, and then intuitively you know that loads have to be passed through that glued connection. Okay, so when we look at this section through here at A, you can imagine that you've got the right-hand side kind of, if you like, glued to the left-hand side. Not really, it's a continuous material, but you can imagine it as that. And then at that section, you've got the loads being generated. And they're they're the internal actions that we're trying to determine. Okay, so let's continue with the problem now. All right, so now that we've got our external loads showing, we need to think about what's happening internally. So for a two-dimensional problem, we'll have potentially a normal force, shear force, and a bending moment. All right, so we need to look at the external forces that are acting on this part of the body that we're looking at and use the equations of equilibrium to work out what these internal actions are, just like we did for rigid body equilibrium problems that we've done previously. Okay, so we need to put on some arrowheads on our free body diagram here. Now there's a positive convention that the textbook makes use of. So in all of my problems, I make use of the positive sign convention that the Hibbeler textbook uses. And that is to say that so we're looking at the right hand and left hand incidence face. what happens if they're vertical. If it's a vertical component, is a bit tricky, but they talk about positive and negative incidence face. So this is actually what they call the negative incidence face. And the positive for normal force is in tension, so acting out of the surface. Positive for shear force is acting upwards, and moment is clockwise. If we looked at the left-hand side of this structure and looked at the left-hand side of the component, we would have equal and opposite of these, and you will see that in a second when I get to that. Right, so now that we have these shown, we can start to write our equations of equilibrium. So sum of the forces in the horizontal direction equals 0. So we can easily see here that N equals P. If P was acting to the left, then we'll get N as a negative value, which would indicate that this is in compression. Right? But because it comes out positive, because we've drawn our arrowhead acting out of the member, directed out of the section, then because it's positive, we get an indication that that's tension. And then shear force, sum of the forces in the vertical direction equals 0. So we have V minus W times A. So the amount of distributed load that's acting on the section that we're looking at. So here it's just W times A. And that's in the negative direction, plus RC, which is our reaction force out on the roller support. Substitute in for what we had before for RC, and we get that the shear force is equal to minus P on 2. Then if we do moments about the cut end, so normally we take moments about the cut end. You can take moments about anywhere else if you like. The only problem is that you'll get V, the shear force, in your equation, and then you just got to substitute from what you found before. No big deal, but you might as well take moments about the cut so that V doesn't appear in the equation. All right, so we have the moment, which is clockwise, so negative RC times A, tending to rotate anti-clockwise about point A, so that's positive. And now we have to do the resultant of the distributed load that's acting on just the section that we're looking at. So now we have W times A, and it acts at the center of this section, so at a distance of A over 2. So we can put that into our equation. WA times A over 2, tending to cause a clockwise rotation about point A, so therefore negative. P passes through point A, so that doesn't cause a moment, so we can put all that equal to 0, and we get M equals this if we rearrange the equation and substitute for RC. So we just substituted that into here, rearrange the equation, do a bit of simplification of the equation, and this is what we get for the moment. All right, so these are our internal actions generated at point A. Right, so as I said, let's now have a look at the left-hand side and see what happens. So same thing again, draw the left-hand side of the section though, put on our external loads. So we've got the distributed load, and we've got our reactions that we calculated at the start from our rigid body equilibrium of the whole component. Put on our internal actions, and now this is what is called the positive incidence face. And there's a positive convention for how we draw the internal actions here. And for the normal force, so this is the easiest one to understand. So again, we draw it acting out of the section to indicate that it's in tension. If we get a negative value, that'll tell us it's in compression. Shear force acting downwards is positive on this face, and moment anti-clockwise is positive. Okay, so these are equal and opposite to what we had previously. And I'll show a picture of that again as we get to the end just to compare. All right, so now we go through the same process again. We know we're going to have to deal with the distributed load, so let's find its resultant. W times A, again, acting at a distance of A over 2. So at the center of the uniformly distributed load. Sum of the forces in the horizontal direction equals 0. That shouldn't be P. That should be RBX. Well, it ends up being P, but let's just put that in. And then sum of the forces in the vertical direction equals 0. We have RBY minus W times A minus V equals 0. Substitute for RBY that we calculated on our first page when we did our original equilibrium of the whole thing. Rearrange that and we get V equals minus P on 2. So far I think you can remember that this is what we had previously. And then taking moments about point A again. So this time the moment is anti-clockwise, so it's positive. WA times A over 2, the moment effect of the distributed load about point A. And then we have RBX times A. So RBX, perpendicular distance to A, tending to rotate clockwise, is negative. And then RBY, acting up here, distance of little a from point A, tending to cause clockwise rotation also. So that's also negative. So rearrange that, substitute in for our values for RBX and RBY, and we get hopefully the same answer that we had before. Missing an A from that equation. So that's a good idea to check. You can see here I've got my equation correct, but I just haven't multiplied by A here. So let me fix that up. So this is a good indication for why you should always check your solutions. All right, put that in there. Now that I've fixed up the previous page, we get the same answers for the moment. And if I go and repeat what we've just done here. So this is what we found by looking at the left-hand side. This is what we found by looking at the right-hand side. So these internal actions here must be equal and opposite to these internal actions over here. Again, following Newton's third law. And this is analogous to what we did with frames and machines when we looked at the pin-connected members. When we imagined that we separated the two components and we draw the two forces from the pin connection. On one side, we drew equal and opposite to what we drew on the other side of the connection. And there are our values for the internal actions at A. All right, so as I said at the start, what we now do with these internal actions would be to use them to calculate the stresses. So for example, this will be in bending. So we'll have stress from the bending will be equal to my upon I. There will be an axial stress, normal stress from the axial load, or the normal load. So we'll have N over A, and we'll also have shear stress. So there's an average shear stress, which is the V over A, but for a beam in bending, it will actually be this equation, VQ upon IT, which we'll look at in later analysis of beams. Okay, so that's the end of the problem. Hopefully you're able to follow through that and understand what I was doing. It's important that you take your time, draw your free body diagrams, justify your equations, and as you saw, check your answers to make sure you haven't left anything out of your equations and final answers. All right, see you in the next video. Bye.